In this lecture, we will learn the unipolar type of logic family, that is the NMOS, PMOS, and the CMOS. CMOS means the complementary MOSFET. Why it is called unipolar, I already discussed in the previous lecture, because the majority carrier of the NMOS is electron, that is only one type of polar charges are there. And for PMOS, that is the holes. And for complementary MOS, the PMOS and NMOS are used in this type of circuit. So for NMOS, the majority carrier is electron, and for PMOS, the majority carrier of holes. So for this reason, this is called the unipolar type of logic family. So if I go first to the NMOS type of logic circuits. So in this lecture, I already told you that we will know the NMOS logic gates, advantage and disadvantage of the NMOS, advantage and disadvantage of the PMOS and the PMOS logic gates, and the introduction of the CMOS logic gates and its advantage and disadvantages. So first come to the NMOS type of logic gates. So in the N-channel MOS family, the current conduction is because of the electrons, we already know, which are negatively charged and fast moving than holes, because the mobility of the electrons is higher than the holes. So for this reason, the NMOS is very faster than the PMOS. Okay. So the MOS transistors, both PMOS and the NMOS, can be combined with the resistive loads to create the single channel logic gates. So suppose this is for an example, this is an inverter where the load resistance are connected with the power supply, and the NMOS are the driver, acts as a driver of the logic gate. Okay. So now first, when we use the NMOS, so then the resistance was used as a load. But for the fabrication issues, the area of the resistance is very high, and it is also the noise prone and non-linear. So the non-linearity effect, the power dissipation and the heat generation and the large area, active area needed to fabricate the resistors in a circuit, we are not using these resistors in future. So then we will use the only NMOS or the PMOS or both the NMOS and PMOS in the logic circuit to make the larger circuits in a single chip. So what is the disadvantage of the resistance where we use? That is the high power dissipation, the heat generation, the nonlinearity effect, and the noise prone device element, noise prone element. So for this reason, we are not using this resistance R. So in the most logic design situations, the power supply voltage is predetermined by either the technology reliability constraints or the system level criteria. This power supply for the ICs is maybe maximum 12 volt. In general, it is the 5 volt. Okay. And another parameters is that where we use this MOSFET, the NMOS or the PMOS, it depends upon the aspect ratio. Aspect ratio means the width of the channel and the length of the channel. Hope you already know the MOSFET, where the N-channel MOSFET and the P-channel MOSFETs are there, by which the NMOS and PMOS nomenclature was done. So this length of the channel which are produced from source to drain, then this channel aspect ratio, that means W by L, width of the channel and the length of the channel, this is the main design issues of the NMOS or the PMOS. Okay. the circuit designer is limited to altering the circuit topology and the width to length ratio, that is called the aspect ratio, since the other factors are dependent upon the processing parameters. Processing parameters means the fabrication parameters. We begin our study of the MOS logic circuit designed by considering the detailed design of the NMOS inverter with the resistor load. Now, if we put, first of all, we should know the NMOS have the positive threshold voltage. Yeah. So if we put the logic 1 into the gate of the NMOS, then the NMOS will be activated. So first we should know as when the NMOS will be activated. First we should remember that if we put the logic high voltage, that means the logic 1 at the gate of the NMOS, then the NMOS will be activated due to the positive threshold voltage of the NMOS. So now if we put logic 0 here, so then the MOS will not be activated. So then there no current will be flowed through the VCC to ground. So we will get the V0 as VCC. So that means if the input and the output of the truth table, so if we put the logic 0 at the input, then we will get the logic 1 at the output. Now, if we put the logic 1 at the input, then what happens? Then the NMOS will be activated. So then the current will be flow through the R and the NMOS to the ground. So we will get the V0 as logic 0. So then the output will be logic 0. So basics of the NMOS type logic gate is that the NMOS are connected as a driver of the main circuit, and this resistor acts as a load which is connected to VCC. But due to disadvantage of some resistors, we should connect the NMOS again at the load and connect it with the VCC. I will discuss in the next slide. So now this is the NMOS NOT gate where we replace the resistance with the enhancement type NMOS. Okay. If the two MOSFETs Q1 and Q2 acts as the Q1 acts as the load MOSFET and the Q2 is the switching MOSFET or the driver MOSFET. Now, since the gate of the Q1 is connected with the supply VDD, then the MOSFET Q1 is always on due to the channel is always on with the source and the drain. And if it is the positive voltage, so it is the upper cut top of the threshold voltage of the NMOS. So then the NMOS will be always turned on. So if now the question arises, how it is always turned on? The answer is the gate and the drain of the Q1 is connected together with the VDD. So for this reason, the logic 1 is connected to the gate, and the channel is already exists in between the source and the drain, and it crossed the cutoff of the threshold. So for this reason, this Q1 is always turned on. Now, if we put the logic 0 here, then the Q2 will be turned off. Okay. So if the Q2 will be turned off, so then there is no current will be flown through this Q1 and Q2. And as the Q1 is turned on, so then V0 will be VCC or VDD as logic 1. So this will be logic 1. So if this is 1, then the Q2 will be turned on, and then the current will be flown through the Q1 to Q2 to ground. So the V0 will be logic 0. So this is the basic principle of the NMOS inverter. This type of 2 MOS are used as the enhancement mode MOSFET. You can use this MOSFET as the depletion type MOSFET also, but the operation will be the same. Okay, so this is the symbolic representation of the enhancement, and this is the symbolic representation of the depletion type of NMOS. This is the symbolic representation of the depletion type of NMOS. Okay, so this is the enhancement, this is the depletion, but the operation is same. The internal resistance of the Q1 acts as the load resistance. Okay, for this reason we replace the load resistance. Compared to both the MOSFETs, the Q1 is designed to have more resistance than Q2. It have the internal resistance is more and than the Q2. Okay, so the internal resistance of the Q1 is higher than the internal resistance of the Q2. So now this is the basic operations which I already described. So now come to the NAND gate operations. In general, you should remember that for any AND operation, the NMOS are connected in series at the driver side. Please note it down. For any AND operation, the NMOS are connected in series at the driver section. Okay, and for any OR operation, the NMOS are connected in parallel in the driver section. So this is called the driver section. Okay, and this is called the load section. So in the driver section, for designing the NAND operation, so first we think this is the AND. So then the NMOS are in series connected in the driver section. Okay, so in this circuit, here the 3 N-channel MOSFETs Q1, Q2 and Q3 are connected, where Q1 is the load resistance, Q2 and Q3 act as the switching MOSFET. So the inputs A and B are given to the MOSFET Q2 and Q3. Now put the 0 here and 0 here. What happens? This Q2 and Q3 are turned off, because we know if we put the upper threshold, positive threshold as logic 1 at the gate of the NMOS, then the NMOS will be turned on, otherwise off. So here this is 0, 0. So for this reason Q2 and Q3 are turned off. So for this reason we will get the V0 as VCC. Due to this Q1 is always turned on. So at that point, at that node, the voltage is VDD always. So now this is VCC or VDD. So now we will get the output at logic high. Now if any one of these, suppose this is 0, this is 1. So this will be off, this will be on. So then there is an open circuit. So for this reason, the output will not transfer to the ground. So then we will get the high output voltage. So this is how high. So now if this is 1, this is 0, the similar case happen is also open circuit with the to the ground. So for this reason the output will not be changed. Now if this is 1 and this is 1, So then both the transistors Q2 and Q3 are turned on. Then the VCC will get a path to the ground. So the output will be logic 0. Or the current will be produced from VDD to ground through the Q1, Q2 and Q3. Then the V0 will be logic 0 or low. So this is the basic operation. If any one of these NMOS will be activated or turned on, then the output will be high. If both the transistors will be turned on, then there is a path in between VDD to ground. So the current will be produced through VDD to ground through Q1, Q2 and Q3. Then the output will be logic low. So this is the basic operation of the NMOS NAND gate. Now, this is the basic operation. Now, the NMOS NOR gate. I already told for any OR operations in the driver section, the NMOS are in parallelly connected. So if these Q2 and Q3 are parallelly connected, and if both the input of the transistors are logic 0, then we will get the V0 as VCC. So there will be no path in between VDD to ground. So the V0 will be VCC or logic high or VDD here. So this is logic high. Now if any one of these transistors will be turned on, then what happens? Any one. So then the current will be produced like this. If this is on, so then the V0 will be reduces to 0. So then we will get the logic 0. Now if 1, 0, then the current will be produced like this. So then also the V0 will be logic 0. And if both the transistors are turned on, then also the same path. So the current will be flow through the VDD to ground through the Q1, Q2 and Q3. So then the V0 will be logic 0. So this is the basic NOR operation. Okay. So now the advantage of the NMOS, if we use, the number of diffusion steps required is the lowest, hence the cost per the gate is lowest. Low power dissipation at the order of nanowatt. Power supply can be varied 5 volt to the 15 volt. Only the NMOS transistors are used, no isolation island are required. Hence the highest packing density of the all logic families. Highest packing density. This is very much important for the NMOS logic family. So the larger fan out capability, maximum 20 gates, will be driven by a single gate output. So the very high noise margin, industrial atmosphere, it is suitable. MOS circuits are used as capacitors, so they can also be used as the resistors. So you can use the NMOS or PMOS as a resistor or a capacitor. In the VLSI in 6th semester, you will learn how the MOS is used as a switched capacitor circuit. So the MOS devices are used in charge coupled device also, CCD, which are used in the camera. The disadvantages, the MOS transistors are also the capacitors, and the speed of operation is lowest due to the very high capacitive loading. Large propagation delay, this is the disadvantage. Higher power dissipation than CMOS. This technology has not acquired a much popularity as the CMOS technology. We will come in the next section. The CMOS, because of its lower power dissipation and the higher speed of operation, the CMOS is used. Okay. So now come to the PMOS logic gates. So here the PMOS NOR gate, the PMOS are used as the load of the logic gates and the resistance is used at the driver. Okay. So for the PMOS is connected with the VDD. The logic operation or the any logic gate preparation, you should remember as the NMOS, that if we design any OR operation, then the PMOS is connected in series. For any OR operation, the PMOS is connected in series. Or for any AND operation, the PMOS is connected in parallel. Just reverse of the NMOS. Okay. In the NMOS, for any NOR operation or operation, the NMOS are connected in parallel at the driver side. Okay. But for any PMOS, for any OR operation, the PMOS are in series at the load section. Okay. So this is the basic difference and the operation is same. But the PMOS have the negative threshold. So for this reason, if we put logic 0 at the gate of the PMOS, then the PMOS will be activated. So this is the basic difference of the NMOS and PMOS. NMOS have the positive threshold to create the channel. Due to the inversion layer will be produced if we put the positive voltage at the gate. So for this reason, the logic 1 will be applied to activate the NMOS. Similarly for PMOS, to get the inversion or the producing the channel, then we should put the negative voltage at the gate of the PMOS. So for this reason, the PMOS have the negative threshold voltage. So due to this, we should put the logic 0 to activate the PMOS. So the basic difference is that if we enable NMOS, then we should put the logic 1 at the gate. If we want to enable the PMOS, then we should put the logic 0 at the gate of the PMOS. So now go to the operation. So now if we put 3 stage, this is the basic configuration of the NOR gate. Now if both the input is 0, 0, then what happens? Then both this MOS and this MOS will be turned on. So then there is a path, current path exists from VDD to ground. So then the output will be, if this is 0, if this is 0, the output will be, this is a NOR gate. If this is 0, both the on. Okay. So then the output will be logic high, because the high resistance of the R, the output will not be transferred to ground. Okay. So for this reason, we will get the output is logic high. Clear? Confusion will be arise that if the current will be produced from VDD to ground, why it will be high? Because due to the high voltage of high value of the resistance R and the low resistance of these two PMOS, then the output will be logic high. The output will not transfer from output port at this node to ground. Okay. Both the PMOS will switch on as the gate input is logic low resulting the creating path for the flow of the current VDD to ground. As a result, the direct path between the VDD and output is established. Thus, the output 0 becomes logic high because due to the high resistance of the driver. When any one of the, suppose this is 0, this is 1. So then the open circuited. Then the open circuited, the load section. So then the output will transfer through the R to the ground. So the PMOS having the high gate input switches off and the other PMOS is switch on due to its gate input is logic low. Thus the current conducting path from the VDD to ground breaks and the ground becomes directly connected to the output. So for this reason, the output will be low. So the output will be transferred to ground. So for this reason, the output will be low. Now for the last stage, that is both are high. Then also both the transistors will be off. So the direct path will be exist from output to ground. So the output will be logic low. So this is the NOR gate. Now if we come to the NAND gate, for any AND operation, I already told the PMOS are connected in parallel. So now if we go to the direct 0, 0 input, 0, 0 input, so then both the transistors will be in turn on. Okay. So similarly, there is a path will be exist from VDD to ground, but due to high value of the R and the low value of the internal resistance of the transistors, then the output will be logic high. Now, if any one of the transistors will be turned on, then the same operation will be produced as before, like this is the off, this is the on. Then due to the low internal resistance, the VDD will transfer to the output and it will not go through this R due to its high value. So then we will get as high. So for the NAND operation, if we put, these are the inputs, suppose this is A and this is B, two inputs, and this is the output. So if this is 0, 0, A and B both are turned on, then we will get logic 1. If anyone turn on, then we will get the logic 1. And if both the turn off, then what happens? Here, if both the turn on, then 2 are off, then the output will get the direct path to ground, then the output will be low. So then the output will be 0. Okay. So then the output will be 0. So this is the basic operation of the PMOS logic gates and the NMOS logic gates. Now there is some advantage and disadvantages. The PMOS fabrication area is very much larger. The power dissipation is higher. Okay, there is a resistance is used. So for this reason, we should go for the CMOS operation where the propagation delay is less, power dissipation is less, and the speed of operation will be high. So we should go for the complementary MOSFET. This is very much important and which is used in the VLSI logic circuits. So this is the complementary MOSFET. Why it is complement? Because here the PMOS network and the NMOS networks both are used. PMOS networks are used in the pull-up network because the PMOS is used to get the output as high. The logic 1 will be very easily transferred to the through the PMOS. So for this reason, the PMOS are connected with the VCC as a load, and the logic 0 will be very easily transferred through the NMOS. So for this reason, the NMOS are connected as a driver. For the NMOS logic circuits also, we see that the NMOS are connected in the driver section. That is called pull down section, where the output will be pulled down to the ground or the 0. And the PMOS are used for the pull up network, where the output will be pulled up to the VCC. Pulled up to the VCC. So the basic knowledge should you have that in the pull up network, the PMOS are used. In the pull down network, the NMOS are used. Yes. So now for any, there is some confusion, I should clear it. So for any pull up network is made by PMOS. Pull up network is made by PMOS, and the pull down network is made by NMOS. Okay, and why it is PMOS is connected to VCC, because the logic 1 will be very much easily transferred through this PMOS, and the logic 0 will be transferred through this NMOS. So for this reason, to get the lower output, we should connect the NMOS network to the ground, and for getting the higher output, we should use the PMOS as the connected with the VCC. Now you should keep in mind, for any AND operation and the OR operation, for any AND or the OR operation, if I write simultaneously, then it will be very easier. For PMOS and NMOS. So for any AND operation, the PMOS should be in parallel. And NMOS and PMOS for OR should be in series. And for NMOS AND operation, it should be in series and it should be in parallel. This is the basic principle. Okay. So now if we come to the CMOS inverter, then what happens? In the CMOS inverter, if we put the logic 0 and logic 1, so if we put the logic 1 here, so then this Q1 will be turned off and this Q2 will be turned on. So the V0 will transfer to ground and we will get the logic 0. If this is 0, then this will be turned on, this will be turned off, then it will be logic 1. Okay. So this is the basic principle of the CMOS inverter. Now if we come to the NAND gate. So for any AND operation, the PMOS are in parallel and NMOS are in series. Okay. So now if we put the operation, suppose this is A and B both are 0. Then what happens? These two PMOS Q1 and Q2 are turned on and these Q3 and Q4 are turned off. Okay. So then the VCC will come to the output through this Q1 and Q2. Then you will get the logic 1. So if the 0, 0 input, then you will get logic 1. These are the inputs A and B, and this is the output Y. or the V0. Here the V0. So if this is 0, 0, then you will get logic 1. Suppose if this is 0, 1. So then this Q1 will be turned on, Q2 will be turned off. So this is 0, this is 1. So for this reason, this Q1 will be turned on, Q2 will be turned off. Similarly for Q3, this is the NMOS. So Q3 will be turned off due to this 0. And Q4 will be turned on due to the logic high at the gate. So this is the open circuited. So then the VCC will transfer to the V0 through the Q1. So we will get the logic 1. So if this is 0, 1, then we will get logic 1. So now if this is both are, or suppose this is a 1, 0. 1, 0 means what happens? If it is 1, 0, then Q2 will be turned on and Q3 will be turned on. But Q1 and Q4 will be turned off. So the same case will happen as before. So for this reason, we will get V0 as VCC because VCC will transfer through the Q2 and then we will get the logic 1. Now if both are 1, then both the PMOS Q1 and Q2 will be off and Q3 and Q4 will be on. So then you will get the output as logic 0. Okay. So then we will get the logic 0. So this is the basic operation of the NAND gate. Depending upon the off or on state of the PMOS transistors and the NMOS transistors. But you should remember the only one things I repeated again and again, that for any AND operation, the PMOS are in parallel and NMOS are in series. For any OR operation, the PMOS are in series, NMOS are in parallel. Then all the circuit design will be very much easier. Now for the NOR gate. Similarly, the two PMOS are in series and two NMOS are in parallel. So here, if both the input are 0, 0, then both the transistors will be turned on. Then you will get the V0 as equal to 1. So if this is 0, 0, then you will get 1. If any one of the input, suppose this is 1, this is 0. Sorry, this is 0, this is 1. So then what happens? This is on. And if this is 1, so then this is on. So this is open circuited. But the output is connected to ground. So the output will be logic 0. So if any one of the transistors of the NMOS will be activated, then the output will be transferred to the ground. So then you will get the output as logic 0. So now if both the input are 1, then both the transistors are, PMOS transistors are in off state. So for this reason, the two NMOS transistors will be turned on and the V0 will transfer to the ground. So then this will be 0. So this is the basic operation of the NOR gate. So this is the total conclusion of the logic family. That is the unipolar logic family. This is the PMOS, NMOS and the CMOS. Now homework is, suppose we want to design Y is equal to A into B plus C bar. Then you should design like this. Here this is the B plus C are the OR operation and A is the AND operation. So what is the configuration of the PMOSFET? Pull up network. A is ANDed with B or C. So A is ANDed with B or C. any OR operation, PMOS are connected in series. For any OR operation, PMOS are connected in series and it is connected with pull-up network. And for any AND operation, it is connected in parallel. So for this reason, this is A, this is B, this is C. Okay. Now the pull down network. So pull down network should be connected with A and B plus C. So that means the NMOS A will be connected with the series with the two parallel NMOS B and C. So this is B, this is C, and this is ground, and this is A. And in between these two, this is the pull-up network and this is the pull-down network. So in between two, we will get the Y. And Y should be in complementary in nature. So this is the basic logic design of a complicated design. Okay. So you should first consider.
স্যার ওয়াইটা কমপ্লিমেন্টেড কি করে হলো সার্কিট থেকে ব্যাপারটা বুঝলাম না আরেকবার একটু এক্সপ্লেইন করবেন
all output is in complementary manner for any CMOS design. You from the NAND gate you design the AND operations, but you will get the NAND operation.
Yes.
So the complementary output,
Yes.
actual circuit output is AND, but you will get as NAND for the CMOS.
Yes,
so
I got it.
For this reason, it is complementary. So if there is no complementary, then you should put a inverter at the output of the circuit. Suppose if the design circuit would be A into B plus C, A into B plus C, then using the CMOS logic style, then you should put an inverter at the output. Then you will get the inverted output. But if it is given, then you should design only the A into B plus C because the output is in complementary nature of a CMOS. Clear?
Yes, sir, clear.
Okay. So now the homework is, number 1, Y is equal to A dot B plus C 1, and another is Y is equal to A plus B plus C into D plus E bar. If you practice these two, then the concept will be clear. Okay. So this is the basic principle of the CMOS logic. Okay. So